Assalamu alaikum students. Today is our third lecture of week 2, and in this lecture we will discuss the different reactive modes. In the last lecture we just take the overview of the radioactivity and the different three modes, and in this lecture we will go in the more detail. So alpha decay was I think already we already understand in the last lecture. So we will start from the beta decay today. So the beta decay occurs when the nucleus emits an electron or positron. As I already told you, the beta decay is further classified into three processes: beta plus decay, beta minus decay, and electron capture. So here is the example of beta minus decay, or it is also called the negative beta decay. You can see the parent nuclei of carbon is converted into the nitrogen with the emission of electron and a neutrino. So the important thing is that the A number, the mass number, remains the same for the parent nucleus and the daughter nucleus, which means that we have only the conversion of a nucleon within the nucleus. So we don't have a change in the mass number. And in the other scenario, we have beta plus decay, in which we have a positron emission and some antineutrino or neutrino. The final nucleus still have 14 nucleons, but it has one more proton and one fewer neutron, which means that the excess number of neutrons, the neutron is converted into the proton. So in this beta decay, we have a conversion of the nucleons. The excess number of nucleon is converted. So this decay is an example of the interaction that proceeds via the weak nuclear force. So negative beta decay in more detail, if we see this electron or beta minus particle is the ordinary electron, and from where it comes, this is the question, because we don't have any electrons within the nucleus. So this electron in the beta decay is not an atomic orbital electron. It is created in the decay process. The need for a particle such as the neutrino or antineutrino was discovered through analysis of energy and momentum, and in the early stages of the beta decay discovery, these were not detectable because they were highly penetrating and have very less mass as compared to electron. So energy, the Q value, mainly shared among the electron and the neutrinos. So in the positive beta decay, the scenario is a little bit different, and the positron is emitted from the nucleus, and the mass number A again remains the same, while its charge number decreases by 1. So the positron is the antiparticle of the electron, and due to this emission of the positron, we call this a positive beta decay, and we have also emission of neutrino in this process. So in this process, again, excess number of nucleons are converted into other nucleon species. So the third one is the electron capture, in which a nucleus captures one of its inertial electron and absorb it, and it is opposite to the beta emission. And the example of this is, you can see in the figure, the parent nuclei captures an electron which converted then into the lithium plus neutrino. As it is involved the capture of the electron, that is why it is called the electron capture. This is one of the example of also beta decay. So you can see also there is a conversion of excess number of nucleon. A number is same, or Z number is changed from 4 to 3, so we have less number of protons in this process. The proton is converted into neutron. So questions about beta decay, as I already told you. So what is going on within the nucleus is the internal conversion of neutrons and protons. The excited nucleus comes to the ground state by the internal conversion, or its changes its excess number of nucleons. So you can see within the beta minus decay, neutron is converted into proton with the emission of electron. Beta minus is the electron, and the ordinary electron, and the proton is converted into neutron with the emission of the positron. So the most difficult question, which was that from where the electron comes if they do not exist within the nucleus. The answer of this difficulty is that the electrons are emitted after just their creation. So these electrons are created; they were not present within the nucleus, means the parent nuclei. It is created from the energy according to Einstein's relation. So the other questions were the electron energy observed during this beta decay is also not like alpha decay energies, which have more or less the same energy within coming from the sample. They make some spectra for minimum energy to the maximum energy. So for a particular one beta decay, or if we compare it with some other decay of the same material, the energy of the electron will be different. So because the energy is shared by another particle, actually it is shared by among the three particles, the daughter nucleus, the electron, and the neutrino. But as the daughter nucleus is the heavy one, so the most of the energy, the 98% or 99% will be energy will be shared by electron and neutrino. So the question was solved after the discovery of the neutrino. So laws of the conservation of linear and angular momentum also seems to be violated when the neutrinos were not discovered. Both the questions were answered after the discovery of the neutrino. So neutrinos were initially not detected, and but after some time they were detected. They interact very weakly, and direct evidence of their existence was not available until more than 20 years has passed after they were predicted. So they were predicted initially that there is some other particle emitted in the beta decay which is not detected experimentally, but it was predicted that it exists, and this was neutrino and antineutrino. So in 1931, the Pauli proposed that if an uncharged particle of less mass and spin is emitted in beta decay together, and this particle is called neutrino. So if similarly the laws of conservation of linear momentum and angular momentum remains conserved, and the problem was solved after the discovery of the neutrinos. Now they are very less massive, and 100 or 200 times the mass of the electron. So still research is going on in this direction. The gamma decay is similar to the X-ray production in the atomic excitations. The gamma rays are similar to X-rays, but they are just electromagnetic radiations. The gamma rays are very high energy photons. When an excited nucleus comes to the ground state, it emits electromagnetic radiation, which is of gamma rays. So normally, usually, after the decay, alpha decay or the beta decay, the daughter nuclei are in excited state, and after this decay, the daughter nucleus comes to the ground state with the gamma decay. So thank you, students. This is all for this lecture. Allah Hafiz.